that's it. So I will be talking about the work that I was doing for like 6 months when I was at Aalto University as like an intern from the ENS Paris. And I want to mention like an acknowledgement the Evelina and also the Leonie who was also here and in Aalto University at some point that she was like helping me with Evelina as well. Yeah, so like what I want to do now is kind of construct the multiple massive SLE curves, and like what I take as a prerequisite because it's kind of junior seminar is more that you know like a lot of things about just the classical one chordal SLE curve and not really about the multiple curves or massive curves. So I was like doing a deep introduction to the multiple theory and to the massive theory. So it will be mostly on an introductory level and not really deep profound. So I'm sorry about that. So I'm starting with the historical perspective. It's that in 2009, Makarov and Smirnov they initiated a program kind of to study the near critical models instead of just critical models with the rescaled parameters. And essentially what they wanted to do is to kind of ask the question, what if we perturb some critical models in some several ways? Could we obtain in the scaling limit something nice in terms of SLE terminology? And they proposed several models, which is massive SLE2 and massive SLE3, 4, and 8. But if you never was looking at it, you shouldn't be thinking about the name of massive, because here in every model the massive kind of means not the same thing. So the models are perturbed in kind of natural way inside the model, and there is no kind of sewing line between the models and how they are connected to themselves. So they are kind of, all of them are massive, but all in different ways. So we will be talking about the massive SLE2. And the starting point is kind of to remind about the simple SLE2 and loop-erasure random walk. So assuming we are on a very simple framework, we are assuming giving some bounded domain on a complex plane. We are taking 2 boundary points. We are taking the square lattice, for instance, square lattice approximation. And what we want to do is to run a random walk from one point on the, our fixed boundary in the domain, which is represented here as a left bottom corner, we want to run this simple random walk and condition it on the event that it exits the domain through the other marked boundary point, which is here, precisely the upper right corner. And what we want to do is we want to take a loop-erasure of this walk and obtain then a simple trajectory, which is kind of, this is probably you already heard about it a lot. So what about this thing is interesting, right, is that if we assume that our lattice domain are converging to the continuous domain in a correlatory way, then we know that our scaling limit is the classical SLE curve, whereas the driving process is the square root times Brownian motion after mapping to an upper half plane. So what we do in the massive random walk is essentially pretty doing the same, but model is perturbed in a way that we are sampling our random walk, but we also have an additional probability for this random walk to be killed at each step. So I've mapped some of the random walks, so the random walk is going, and it could be killed at each point with the probability, start with the classical version of it, so it's fixed probability, which would be the scale on the scale of delta square. So we are just doing a simple random walk. It's doing with a probability of 1 minus m delta square over 4, just a simple random walk, or dice with probability m squared delta squares. What you want to do is you want to sample this random walk and condition it on event that it will not be dead until it reaches the boundary. So it's kind of perturbed massive random walk, because it's now more concentrated on the events that the walk is not killed, where the walk is not killed. So what we want to do is to take a loop-erasure of it and to look what is the scaling limit of this process. And what maybe I want to emphasize that kind of the limit was already predicted by the Makarov and Smirnov in the original paper. So they precisely gave martingale observable. They were not giving a lot of details of really how to prove this convergence, but they already knew what the form of the scaling limit of the massive loop-erasure random walk should look like. And in 2019, the Shelcock and Wong, they kind of filled the gap in the proof, so they gave a complete proof of what is the real scaling limit of the massive loop-erasure random walk. So it's kind of the same as for the simple loop-erasure random walk, which is like after mapping to an upper half plane, right? It's also given by linear evolution with the driving process, which is a martingale part, which is our, again, square root of 2 times Brownian motion, but with an additional drift, which kept coming effectively from the, I didn't mention it, but those curves, they were proven to be absolutely continuous with respect to the classical SLE2. And so after the Pearsonov reweighting type techniques, it could be shown that this additional drift, it essentially classifies the limit itself. And this type of object is called the massive SLE2.
Sorry, what did you say? What the zeta is? Or?
Yeah, I will be saying it right now. Yeah, so zeta has a kind of special form in this way, and I don't. This kind of not really good form of it. So essentially, what this zeta is a kind of ratio between the massive Poisson kernel and its derivative. So our Poisson kernel, it's the idea of Poisson kernel comes from the Green's function, right? The Green's function is simply the integral kernel of the minus Laplacian with the Dirichlet boundary condition, so it's like this 0 on the boundary. It's our classical Green's function, and the massive Green's function is the same, but not for the minus Laplacian, but minus Laplacian plus identity times m squared. This is the massive Green's function. And what is Poisson kernel with respect to a massive Green's function? Is normal derivative. So it's kind of its normal derivative is simply Poisson kernel. And we know the precise formula like in any domain, because we know that these processes, these functions are conformally invariant, kind of conformally covariant in this sense. So like on the upper half plane is simply minus 1 over p imaginary part of 1 over zeta minus x, and then by conformality is like mapping to any other domain. But it's also the same as just taking the normal derivative of the Green's function. And so our massive Poisson kernel in this sense is also kind of this thing. And this ratio is so in the numerator is its derivative with respect to the second variable. And this formula is coming from the fact that like actually we could take in this formula, which is a definition of the massive Green's function, we could say actually that we could multiply by the ordinary Green's function and obtain something like massive Green's function. It's a Green's function minus integral over delta. So it's kind of this type of formula is coming as an like resolvent identity for the massive Green's functions in terms of just simple Green's function, but these things are kind of appears naturally with respect to the massive Green's function. So, and what I want also to mention here is kind of this drift, even though the process now after the diagonal map, right, after the mapping to an upper half plane, this drift is still kind of depend on the point of our curve, like on the tip of the curve, and also of the original domain, and not kind of the upper half plane, because this type of objects, they are not kind of conformally covariant or something, and in fact we should change the mass to kind of obtain something similar to the conformal covariance. So this is just the formula for a drift, and like in the 2021, Beristikian, Schmidt-Sivitz, they are kind of revisited this idea in terms of near critical dimer models and something, when they're assuming they're kind of doing the more profound idea with it, when there is not a constant kind of probability of being killed, but there is a smooth and bounded mass profile of being killed, which is also kind of scales as delta square. And the massive random walk, in this meaning, it dies with probability rho delta, v delta at each point of the lattice domain. And in this terminology, so kind of when the mass is not now constant, but kind of also scaling as delta square, you have the similar convergence, where also the drift is kind of the same form, but now where the masses is on inside of the integral. It's pretty much the same formula, but not for the constant masses and like for the mass profiles.
I was wondering, is there some idea of what, in this very simple case of the lattice, like what happens when the mass is relatively high? Like, does the random walk somehow not curve as much? Or
do you mean like when the mass here rho is kind of?
Yeah. So how are the regions? I mean, here how are the regions different when the mass is higher or lower? But also just in the general, like what?
I believe like this case is kind of the same as the constant mass scaling because of the assumptions on the functions. It's kind of good functions, smooth and bounded, and for the more extreme cases, I'm not really sure about how so the curve is right. The curve is kind of supported on the events, like more concentrated on the events where it's less likely to be killed. right?
I think my question is more simple. Like if you have a random walk on a square between the corner points,
Yeah.
and you don't have any mass, I mean, we kind of know what a random walk looks like.
Yeah.
But if you now introduce this mass, like which paths are more likely somehow to appear?
Because if the mass goes to infinity, would the path be just like
For example.
geodesics?
Yeah,
Because they have to be like very short not to get killed somehow.
Yeah, I was thinking if something like that is true.
I'm not sure.
I think this is a conjecture, but it's not shown.
Okay.
So the bigger the mass, the more straight your path can.
Or yeah, like if you have the massive SLE and you take the mass to infinity, then you would get some geodesics.
But is it true that also like when the mass is small, like
Then the mass goes to 0, then you would get the regular SLE, but I don't know more.
and kind of there's just from SLE to geodesics. That's what the mass does.
Yeah, I'm not sure if it's kind of done.
Yeah, but it's some intuition maybe to work with that somehow. The random walk takes shorter path if the mass is high, because otherwise it can get killed. So,
That's quicker in finance, right?
yeah.
Yeah.
So then it needs to take a shorter path.
Yes.
Because, yeah, okay.
That's like
I was just wondering how to think about this. Then now I can think about how, like, when the mass changes with the space.
Yeah, so maybe when the when the mass is going to infinity, it should be just simply the straight line. Geodesics.
Yeah, I would prefer to say that, because I guess the mass could be like, it doesn't have to be a constant in your domain, maybe. So,
Yeah.
yeah.
Yeah, but I don't think that kind of it was proved, or there is some works on it. I'm not really sure. On a continuum level.
Yeah.
Maybe for the discrete. I don't think so.
Yeah, so here we have bounded mass, so something like...
Yeah.
That probably helps.
Yeah, because this, in the terms of methods that they were using, it's not kind of really far away from the Chalcakant one. So this one is kind of line by line going, kind of the same strategy of proof, the same kind of ideas. So it's not really that different from the constant mass, I believe. I mean, in the proof it kind of seemed to really the same. Yeah, so now after the dive into the massive things, I want to discuss actually the multiple things, because otherwise it will be nonsense. Yeah, so in parallel kind of the other world, the multiple SLE curves were developed. They were like firstly predicted, as I understood, by like the works more on the CFT part and not on the probabilistic part. And it was like just one of the example that maybe, I'm not really sure, that kind of things as multiple SLE curves, they have already appeared in the critical easing model with alternating boundary, because probably like the works on the easing model were before the SLE type things. And so in what I want to define in this setting is kind of, what if like you want to grow multiple curves in the same domain that are not intersecting, but are like each one is the SLE curve. They are not intersecting, but they are interacting. They are interacting, of course. So yeah, the one not like kind of not really crucial, but the notation that is kind of really will be going through the talk is the link patterns. It's just so in the formal definition, it's kind of you're taking the two endpoints on the boundary, and the question is like there is several ways to connect these boundary points in the non-intersecting maniers, and this maniers is precisely the link patterns. So this is the example of link patterns, and all of these link patterns there could be encoded as like a pair of indexes, and link patterns are in bijection with the Catalan object, so like there is a Catalan number of them for the n curves. Yeah, and the problem with the multiple SLE is like it's not the same as the one curve, because in the one curve there is this good kind of two descriptions of the one SLE curve. Like from one point is a curve grown from the stochastic linear evolution with Brownian motion, and from the other part is kind of this configurational definition when like you're having a conformally variant law with domain Markov property on the linear curves, and it's kind of the same. For the multiple curves, it's not the same, so there is a two frameworks, which one is the kind of dynamical, the other one is configurational. We'll be dealing with the configurational, but not with the configurational, but with the dynamical, because we will be working with the scaling limits of the lattice models. But I still said to mention that kind of in the configurational domain, the configurational definition, yes, this is what I was telling about the one curve. So like for the several curves, the configurational definition is the law of each curve conditional on the event that you are knowing other curves. It should be an SLE in the remaining domain obtained by erasing the how to say, the bodies that our curves are the boundaries of. So essentially, the global multiple SLE measure is a measure on curves that are not intersecting, such that each law of the marginal conditional on giving the others is also an SLE curve. And it is known that like it really exists. It exists as some absolutely continuous measure with respect to the independent and chordal SLE curves. And for the local multiple SLE, so it's with the dynamical definition, we need to kind of define, so in this case the curves are really also grown from the linear evolution, but they would be grown only locally in the localization domain. So we are taking the localization domain for each point, and here now we are having two end curves, kind of, so the curves are growing from the two directions simultaneously, and so there is a 2n points on the boundary and 2n curves which are restricted to stay in the localization neighborhoods, and so now the curves would be starting from the boundary point that we already marked. They would end at the boundary of the localization neighborhood, and so our measure is kind of measure on 2n tuples of the oriented curves, and also on the localization neighborhoods. And it should verify several properties. One of it is conformal invariance, the other one is the domain Markov property, but this kind of should be mutual for the several curves. So if you're growing a little bit of all curves at the same time, then conditioning on this event, the rest of the curves should have the, so it's kind of essentially the domain Markov property, but it should happen mutually for the several curves, like if you are doing the implementation of several curves. And also the other one, which is very important property, it should be absolutely continuous. So like this measure, each marginal of this measure, so like each curve, after mapping to an upper half plane, it should be absolutely continuous with respect to classical SLE2 measure. It should be taken as a definition, and so it's absolutely continuous with respect to classical SLE kappa measure, which is started from the boundary point that we already marked, and which is restricted to stay in the localization domain. And after some years of transform things, what we could see is kind of that each curve also could be grown from the Loebner evolution, but with an additional drift coming from the function that is called the competition function in this setting. And this function is kind of believed to describe the geometry of the multiple SLE curves. It's known to verify some as property coming from the conformal field theory as a BPC equation, Merkel's covariance, and all of these things.
So for the AC, was it the law of one curve, of the marginal law of one of those curves?
The law of all marginals. Yeah, the law of each marginal curve is absolutely continuous with respect to classical SLE2 kappa, SLE kappa, the same, starting from the same point and restricted to the localization domain that we already fixed. Yeah, but this one could be taken as a definition, but I decided, to say with the absolute continuity and not with the Loebner evolution. And it's been shown that this function is kind of unique for each margin of each curve. So for the growth of each curve is kind of the drift is coming from the derivative of the logarithm partition function. This concept essentially is one function that describing the law. Yeah, and so for the global multiple SLE, it has been shown by the Peltola and Wu that kind of when restricted on the localization domain, it's the same measure as the local multiple SLE, but the converse is not really true. But there is a way to kind of grow on the full curves from the local curves. When in the several cases when these curves are coming from the scaling limit for the multiple interfaces in the critical models. Because it's not kind of the same thing, it's two different objects. And now what I will be talking about is the discrete model, which is would be converging to the multiple SLE2 measure and is known as the UST boundary branches. So what we want to do here, firstly we are considering our domain, our lattice domain which approximates it. And what we want to do also, we want to add kind of one step from the boundary, I would say. Right, so what we want to do is not now really approximating only the interior, but we're also adding the several points, which is one step from the boundary. I believe it's okay, right? If you're adding one step from the boundary points, and then what you want to say is, actually I want to collapse all this boundary to kind of one vertex, which would create a UST with wired boundary condition. And now what we essentially have, we have the interior points, which they were as it was. We also have the one boundary vertex which stands here, and we also have boundary edges. It's the edges that are coming from the interior vertex to the boundary. So like this interior edges here, the boundary edges here, they're coming here. So now we are having kind of three types of objects, or even four interior vertices, interior edges, boundary vertex, which is one vertex now, and boundary edges, which are connecting the interior points to the boundary point. And what we want to do is we want to sample choosing a uniformly spanning tree. On the graph is a wired boundary condition as here. And we have to notice that kind of in this setting when boundary is wired, not all edges are now presented as it was for the spanning tree. So not all edges are presented here, right? And each interior vertex has a unique path to the boundary, which is known as boundary branch. And there is a key thing in this trick, is that actually this boundary branch is distributed according to the simple loop-erasure random walk law. So this is what kind of the motivation to do it is. Now the boundary branches in the UST spanning in the UST with boundary condition is the kind of loop-erasure random walks. And what we want to do is kind of grow several curves, several boundary branches simultaneously. They will be not intersecting because of this is spanning tree. And what we want to do is kind of we're fixing again boundary edges, right? We are conditioning our tree to have these passes from each boundary edge to other boundary edge, or more precisely from each interior vertex of boundary edge to the boundary via the other boundary edge. And what you want to do, you want to study the limit of the several boundary branches in the same, simultaneously. And these boundary branches, they also could form again some fixed pattern. And so what we want to do now is because of this restriction on the thing that I was talking previously, is that kind of why I'm choosing here the local multipolarity, because the local multipolarity, the linear evolution is presented, and for the global ones, you should understand how the conditional laws are evolutioning in the scaling limit, and I'm not really sure if it's kind of done. So essentially what we want to do is we want to restrict our boundary branches here to the a priori localization domains. So now we have also kind of two-sided curves that are localized at the localization domains. So here I wrote the procedure to rigorously define it, right? But essentially what you want to do here is kind of take a restriction domain, take a localization domain, restrict one, the start part of the curve here, and the end part of the curve here, and now we have 8 curves, which are essentially our loop-erasure random walks. And what the Karylov has proved in the 2020 is if we assume that the boundaries are converging, or not, the domains are converging in a territory topology, the scaling limit of this boundary branch is restricted, they would converge exactly to the local multipolarity measure. With a precise partition function that maybe at some point I would write, I'm not really sure. So, and now I will present the massive multipolarity curves, which is essentially should be combining of two of these ideas. I want to grow several curves. Each of curve would be the massive loop-erasure random walks, and I want to study their evolution simultaneously, kind of using the spanning trees idea and Wilson's algorithm. Yeah, so I'm taking as a formal definition so I'm starting with the model of tree and not the massive random walk, but the idea is to create a tree so that its boundary branches would be distributed as a massive loop-erasure random walk. So the idea that I came with is kind of taking the general finite graph, which is connected, and start with some enumeration of the vertices, which is, so you're starting with the sum enumeration of the vertices of G. They're also giving the mass profile, and the algorithms that I'm sampling my tree with is the following. So I'm kind of start with the first vertex. So I choose the enumeration, I'm kind of start with the first vertex, And then what I want to do is to sample massive random walk from the next vertex, kind of from the phi1 condition to hit the phi0 before dying, and adding the loop erasure of the path that I was drawing. So I'm kind of, so maybe just kind of, the idea, I take some enumeration, which for instance could be something like, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so what I want to do, I'm saying, yeah, my spanning tree would contain the, have to contain the vertex 1, so, okay. Then what I want to do is I want to start the massive random walk from this point, and I would add what I've visited before I'm reaching the 2. So it's kind of the massive, so it's kind of the Wilson's algorithm, like when you're adding the loop erasure of the simple random walk, but here, instead of the simple random walk, you're having the massive random walk, conditioned to survive until it hits the trees that already spanned.
Right, so this enumeration is just the points in the interior of the graph.
No, it's kind of in this setting, it's kind of algorithm on any graph.
Okay.
Yeah, and so one of the key thing in the just simple Wilson's algorithm is kind of that enumeration doesn't matter. You could actually take any enumeration, you would obtain the same law of the tree.
It's true also in this.
Huh?
It's also true in this massive case.
Yeah, it's also true in this massive case, and like so I believe I proved it, and then I also find some paper on like where so I found it on Monday that kind of the similar algorithm is already been studied. It's in the context of also some neocritical dimer models. And so it's, I believe it's something, so I know the name, Luca Ray, I believe. And he wrote a paper on some dual transform of something, and trees and forests. And he essentially, what he have done, he kind of doing the same procedure, and he obtained the precise formula for the law of the tree, and not for the. And because of he obtained the law of the tree, it's not dependent on the phi, so it should be nice.
For your algorithm, does it matter if you for example, already sampled the first loop erase random walk, connect new points, then you do a next one. If there's a loop that eventually touches already the previous random walk, I mean, it gets erased in the loop erasure then. Or does this to get some intuition?
When you touch the previous things, you die. That's how it works in the algorithm, right?
What do you mean? Like you already sampled a little bit of the tree?
Yes.
You are sampling another, but if you already.
But then you die.
No, if you already know that. You mean if you know already that this vertex is already in the tree?
Mm-hmm.
You're just going to the next vertex by enumeration.
Okay. Yeah.
Yes, it's.
Yeah. Then it doesn't. Yeah. All good.
Yeah. So when m is equal to 0, it's the similar. It's just the Wilson's algorithm, and the idea to take it, like as I said already, in the spanning tree on the graph is the wired boundary condition. The law of the boundary branch will not be the loop erasure random walk, but the massive loop erasure random walk. And now I'm returning to our framework. So I'm taking again lattice approximation, our bounded simply geometric domain, our also mass profiles on a lattice that are scaling of delta square. I'm taking the spanning tree, which I denoted here as MST, like mass perturbed UST is mass profile M here. But here the mass profile should be, of course, raw delta, not the, because here the masses are changing kind of. And again, I want to condition this tree to have the boundary branches between fixed boundary edges, and I want to understand like how their law is described. So we have like n curves that are boundary branches that are branching the boundary edges according to some fixed link pattern alpha. And what we want to do, essentially, again, we want to restrict our branches to localization neighborhoods. So we have, again, two-sided curves, which are trapped in the localization neighborhoods. And what we want to do is to understand this measure on two n curves. So essentially, this, because of each marginal is the massive loop-erasure random walk, it should be absolutely continuous, kind of in the multiple case. So multiple branches should be absolutely continuous with the massless branches, as it was for the one curve. So I'm taking the notation this one is the measure on the two n curves that are starting from the boundary edges and are restricted to the localization neighborhoods, and the alpha is kind of saying that we are believing that kind of it should be then completed to the full curves. They would really be grown to the full curves, or because of also like we're starting with the full curves here, and then we restricted them, and the full curves are already pair the boundary edges according to some fixed link pattern. So what we want to do is to study this scaling limit of this measure. And I'm also taking this notation, it should be like the same boundary branches, but not from the MST measure, but from the uniform spanning tree. So it's kind of the same as it was in the Karela. And I can hear that this measure is weakly convergent already to the law of local multiple SLE2 measure. So what already I've proved that essentially the sequence of this measure is tied whenever this massless measure is tied. So essentially when you want to do some, you're taking classically some topology on the driving processes as probably should be done here. And like whenever like you're taking the Karela result and the topology where this probability measures are tied, this will be also tied. And each subsequential weak limit of our sequence of masked measures is absolutely continuous with respect to the SLE2 measure, to the local multiple SLE2 measure on the same localization domains with the bounded Radon-Nikodym derivative, which is absolutely almost surely bound on the density of massive local multiple curves to the massless local multiple curves. And we also have that the measures are mutually absolutely continuous because the density kind of not vanishing to zero at each non-zero measure event. And the step that I'm kind of was trying to go, so the work that I'm on, the work that I'm doing now is to kind of obtain the really not the absolute continuity statement, but exactly the driving process statement. Because if I take local multiple massive curves, or more precisely, because we didn't prove the unicity of the limit, I'm taking any convergent subsequence, and I'm taking already known the convergent result for the local, just massless local multiple SLE2 curves. Each marginals should be absolutely continuous because we proved it already for the several curves. So for the marginals to be true as well, and the density should be as well bounded by the same constant because we could reintegrate it with respect to other curves. And what we want to do with this is we want to consider the martingale of the density. We kind of do Girsanov reweighting of the process by the density martingale. And because of this density martingale is not 0, so it's bigger than 0 almost surely, right? You could represent it as like exponential local martingale with respect to some L. And because of convergence to the local multiple SLE2 measure for the massless case, we already know that the Loevner evolution, that those curves in the massless case, each marginal is coming from the Loevner evolution with the driving process that is a solution to this SDE with the partition function. We already know it because the Karela proved that it convergent to the local multiple SLE2 measure. We already knew it, and then the driving, so for the curve after mapping to also the mapping on the upper half plane, the massive curve should be also a Loevner curve, which driving process it would be, so the driving process of the massive curve would coming from the Girsanov theorem by reweighting the local martingale. So this term we know already, it solves this SDE, and like to identify the driving process of the massive curve, we need to only identify this additional drift coming from the Girsanov reweighting. So what I kind of claim to do is that actually the driving process of the massive curves is the drift from the massless curve plus an additional deterministic drift, which is kind of also of the form of the partition function, but the partition function is different in a way that it's now massive. There is also this kind of melange of two ideas, one which is the massive curves, other one is the multiple curves, and this drift is kind of similar to both of them, because it's kind of the partition function thing, but it also, when taking to the case when n equals 1, it's actually the same Beresty-Hahn-Schmidt-Sibitz drift. Because in this case, so WT is just square root of, in this case, the square root of this one is just square root of 2bt, and this one is essentially the same drift as in the Hahn-Schmidt-Sibitz. And the form of this partition function is actually pretty similar to the form of the Karela has obtained. So essentially what here, what's here stays for the partition function. In the massless case, in the Karela case, what is absent is kind of the mass here. It disappears, and it will be just, so this one is the Poisson boundary to boundary kernel or just excursion kernel. Just for these things, the partition function is zero mass. It's kind of the polynomial in the objects of type 1 over p x y minus x alpha y squared. So it's essentially the same with object, but also taking the boundary derivative of Poisson excursion, Poisson kernel, but now with respect to the second variable. Yeah, so now I want to talk about the proof kind of the absolutely continuity statement. And the proof is kind of, because it's kind of strange, because we were actually would work with the, not with the restricted curve, but with the full curves on a discrete case, and our bound is not dependent on any localization domains. But because this measure is also defining the measure on localized curves, the bound will be also, so it will be uniform in the localization domains. So I'm taking this term, which is a density of massive curves to the massless curves, and I want to prove that it essentially is bounded, two-sided bounded uniformly in curves. So I start with kind of thing that is already probably mainstream, is the things that is kind of equivalent to the crossing annually estimate, is that the number, like expected number of vertices in the simple random walk in the lattice domain is uniformly comparable with r square over delta square. R square is the radius of the boundness, like the of the coming from the boundness of the domain, and it is already probably it's kind of should be a mainstream fact. And what I want to do is kind of take this crossing annular estimate that is already known. I want to take an extension of it for the multiple curves, which is essentially means now I'm thinking not just the simple independent random walks, but I also do want to restrict them on an event that like loop erasures of between each of them, so they are not really, their loop erasures are non-intersecting. And because of, I just could say, actually this one is less than 1, so I have some expectation of sum of independent random variables, and actually just multiplying by n the previous inequality, just multiplying by n, and that's it. And essentially what I want to do is kind of prove the same thing for the discrete, and then in the continuum it will be kind of automatical coming from something very classical. So in the discrete I want to prove that this density found here is really bounded for uniformly in curves. And that would be coming from this crossing annually estimates, exactly in this multiple form, with the restriction of non-intersecting of the simple random walks. So I'm taking two objects which are kind of partition functions for the several multiple curves, and what I want to do, I'm taking an exact value of the density of massive curve to the massless curve, evaluated at each realization of each curve. So this one term is, this one, for instance, term is coming from the, actually the composition of each. So because of this measure this was a density on measure on the non-intersecting curves. And what I'm doing now, I'm writing my probability as just a sum over all curves which their loop-erasure is exactly this non-intersecting curve. Those non-intersecting curves. So this probability that in the, so for instance, probability that in the that our boundary branch is exactly gamma 1 gamma n, right? So this one is the ratio of probabilities that in our massive tree our boundary branches are exactly gamma 1 gamma n, and this is exactly as just simply write as a sum over all possible random walks whose loop-erasure are exactly these curves. And what I want to do now is to prove that this kind of thing is bounded from above and this logarithm is bounded from below. I'm saying that, yeah, of course, this thing is just simply less than 1 for the upper estimate, so I have to work on this partition function kind of objects. And what I'm saying is its inverse of this object could be written as just evaluation of the this kind of expectation of the weighted object with respect to the massless one. And what I'm using is here, it's just the fact that actually this thing could be because of the, so I'm doing kind of approximation with R delta Z delta, right? And then I'm saying that actually, of course, rho at Z is less than infinity norm of the rho. So it should be nice, but there is also this additional term because of the approximation. And like when you have this term, right? This one is, if all of the terms are the same, it will be just this term to the power of sum over all curves, all simple random curves, simple random walks with the loop-erasure are exactly gamma 1, gamma g, etc. And then by Jensen's inequality, what I claim is that this object, so the expectation are coming this upwards, and now this term we know how to bound it, and this term is less than 1, so we could use the estimation for this term and obtain our desired estimate. And for the logarithm, it's pretty much the same idea, and the technique is kind of the same. It's saying that, yeah, this object is actually bigger than 1, of course. So now this term I would again write as a expectation with a massless thing of a massive object, conditioned on an event that our loop-erasure is exactly gamma e, and then just by also Jensen inequality, but with addition things that like condition expectation of the condition expectation is just expectation. I obtain the same, and also the approximation of our rho z. I'm obtaining the same object here, multiplying by some logarithm and then just taking the Taylor expansion of the logarithm. And so, as I told you, those objects and those bounds are for the full curves, not for the localized curves. But because the full curves, the localized curves could be obtained from the local. Full curves could characterize the localized curves, so these bounds are of course true for the localized curves, and the estimates are still valid. And now this absolute continuity statement is coming from the more general theory that's just saying, yeah, actually we have two probability measures. Each measure is absolute continuous with respect to the other one, and the densities are uniformly bounded. Then if one sequence is tied, another sequence is also tied. And because of this thing, that the logarithm is bigger than minus infinity, it means actually that f is not zero on any events that is not measure zero. So the f is more than zero almost surely, and then the measures are mutually absolutely continuous. And now towards the limit identification. So the limit identification is of course kind of not completed at this point, but the main idea that lies under it is essentially the connectivity probabilities that we were conditioning on. So we were conditioning our tree to have the boundary branches connecting our fixed boundary points. And so our objects to obtain the limit identification are exactly these connectivity probabilities. So the probabilities that in the massive spanning tree there is a boundary branches coming from the interior vertices or the fixed boundary edges going to the boundary of the domain, exiting through the outer boundary edges. And what you want to do is to calculate these probabilities. That there is exactly this. So this was exactly the event that we were conditioning on to consider our boundary curves. And what I'm saying is kind of in the same idea that there is those boundary branches if and only if, like, so it's the same probability as consider the independent massive random walks to go exactly through from one point to another mutually for all g. So what I mean here is like in the massive spanning tree there is a boundary branches that pairs the boundary edges. It's the same probability as massive random walks are going from this edge to this edge, and their loop-erasure are not intersecting. So it's kind of the same probability, but also with an additional term that each massive random walk should not be cubed. And this term, it's also the renormalized term because here the massive random walks, they were conditioned to survive, and this one is the normalization constant. And this thing is actually our zeta rho delta that we found that we are considering here. This is precisely this object. Right, so this one was the probability that there is a boundary branches. So the probability that massive random walks are branching the boundary point according to the link pattern, and also they are not intersecting in the sense of their loop-erasure. And so what I wanted to do, right, is to calculate this object in terms of simpler objects. So what could we do? And to obtain this formula, I would use the Fomin's lemma, which was kind of in the same spirit that it was done for the just the UST measure. It essentially says that if we are taking the determinant of the discrete Green's functions on one side, from the other side it would be a sum or the symmetry group of any elements times signature of the permutation times the weights of the sum that's going from for all admissible curves that branches one point to another and their loop-erasures are non-intersecting. So in our case, it's could be usable because we could take just the edges, so we could assign the edges to have a weights, which coming from so edges could be oriented, then the weights coming from the vertices. All right, and what we want to do is to say that actually this one is our object. That was the probability that there is a boundary branches that pairs the boundary edges according to link pattern alpha. It's actually the same. It's of the same form as it is down here. So essentially, what I want to write is to say that actually my determinant of the Green's function, which are actually massive Green's function, on the left side is the sum over our probabilities that there is a boundary branches that pairs the edges according to the link pattern alpha, but sum is going not for the alpha, but for the alpha to the power of delta, which essentially means that you kind of acting by permutation on the second vertex, second index here. So essentially, what is going on here is you have the determinant of the Green's function on the left side, and on the right hand side you have the probabilities that in the massive spanning tree there are boundary branches that branches according to the link pattern alpha. This object is also dependent on the link pattern alpha because it's written here. So on the left hand side you have some determinant thing, which is dependent only on the branch, on the boundary points and on the link pattern. And on the right hand side you have the probability that depends on the also on the same boundary branches, also on the mass, but here the mass is also coming from because of the definition of the weights, which are also dependent on the rho, so it's kind of the same thing. And the idea is kind of that is hiding here is actually these two objects are the basis on the spaces of on the vector spaces that are isomorphic to the R to the power of link patterns for n curves. So essentially what I want to do is to inverse this matrix and to say, actually this big probability, it's just some possible coefficients which are depending on the link patterns with the determinants of the Green's function. And why it is good? Because for the Green's function we know how it behaves in the scaling limit, even if the points are on the near the boundary. Still, this object was kind of bad and strange because of the multiple conditions to several curves should not intersect and all these things. But the main goal of all these things was to obtain this formula, because in this formula this is the determinant of the simple Green's functions, and the Green's functions we know how they are behaved in the scaling limit. So I wrote here a kind of the martingale observable that I want to use to prove the convergence toward the to identify exactly the drift. So yeah, so it's still kind of in the I would say in the preparation, but because of the connectivity, because of the fact that our martingale, like our limit identification, is based on the connectivity probabilities, and because of the structures of these things, this object should be a martingale, which is obtained from reweighting one curve martingale obtained by Hausdorff-Schmidt-Sievetz. So it's essentially coming from the reweighting one martingale, which was for one curve, by the density of the n curves, and then obtaining some martingale observable, and this object is coming to the it's not dependent on the lattice and like on the variation of these things, it's just a normalization. Because of this is the determinants of the Green's functions, but actually it's not exactly the Green's function because the points are on the boundary, so it has not the similar scaling limit behavior, so it should renormalize these things to the thing in the bottom. Yeah, and yeah, just to maybe recall, and so yeah, it's actually this matrix. So this object is precisely the continuous counterpart of the object that is described here, because this one. Because this one we know how to write it in terms of the determinants over the Green's functions, the massive Green's functions, and we know how the massive Green's functions are evolutioning. So this object is kind of believed to describe the multiple massive SLE2 curves. But of course there's some kind of difficulties in the proof of it, because essentially, so what I was obtained as a critique from the Leonie is that she told me that yeah, you need to prove that this is indeed a martingale, and the problem is also kind of coming from the fact that for one curve they were not proving that this is a martingale, and it's kind of not really clear of why it should be a martingale. So it should be because, for instance, for the rho, right, when the mass is changing, the walks are not reversible because now all edges are oriented. The walks is not reversible. The kind of classical argument probably is not very good. But for the n curves, so I do believe that I know, if I know that one curve martingale, if I take one curve martingale, I could transform it to the n curve martingale. So yeah, and so I was thinking to address kind of the critique that I obtained, but because Leonie is not here, I will not do it. Yeah, probably that's it.
Okay, thank you.